Hello, class. Welcome back. This is lecture 6. Today we're talking about the law of total probability and Bayes' rule. So first off, let me remind you of a little trick that we've used. So we've referred to the following a couple times for events A and B, and that is that you can think of an event A as broken into two pieces, the parts that are in B and the parts that are not in B. So that's what this is saying. We can union those two parts together to get A again, but this breaks A into two disjoint pieces, which breaks A into disjoint parts, those in B and those not in B. So visually, real quick, you can draw what's going on here. So this is sort of like the stuff that's not in B. So that would be A intersect B complement. And then the stuff that is in B here, that's A intersect B. So you can break A into those two pieces. If you put them back together with the union, you get A, and they don't have any overlap with each other. Okay, so then this is actually a special case of something more general. So we want to generalize. The property that we want to generalize has to do with B and B complement. So the property to generalize is that the main thing that makes this work is the fact that B and B complement together make up the whole sample space, and they have no intersection. So these are the main properties we want to generalize, but instead of just thinking about two sets, B and B complement, we want to think about how this would work if I had a bunch more sets that obeyed these properties together. So that leads us to the main definition of the day that'll help us a lot. So the sets, so I'm going to call them B1 to Bn. So the point is just that there's n for some n, some amount of them. And they do something called partition, or they form a partition. You can say it like that too, but I'll say that the sets partition the sample space, omega, if two things, you stick them all together with unions and you get the whole sample space back. So everything is accounted for in these smaller sets or events. But two, they have no overlap at all. They are all disjoint from each other. So there's no overlap between any pair of them. We've written down that property before. So this is in words, but you can write down the little property that I've written before for it. So then when this happens, we can sort of do what we did up here. But instead of just with B and B complement, which is just two sets, we do it with all of these sets. So when you have a partition, and A is another event, then you can think about A as the pieces of A that are in the first set separate from, and then you union, and it's going to be disjoint because B1 and B2 are disjoint. The pieces of A that are in B2, and then the pieces of A that are in B3, and so on until you get to the last set, pieces of A that are in Bn. So it's very similar to breaking up A into B and B complement, but instead of B and B complement, now there's a bunch of sets that make up the whole sample space that are disjoint from each other. So yeah, just to be aware, these things are all disjoint because the B's are all disjoint from each other. So you're just saying, I want the pieces of A separated by which part of the partition they are in. So I want the ones in B1 over here, the ones in B2 over here, ones in B3 over here, and so on. And there's no overlap at all because the partition has no overlap. So that's always good when you can have a disjoint bunch of things union together, because then when you do probability, you can just add the probabilities. Okay, but let's also think about it visually. It looks kind of nice visually. So you might have something like this. So instead of drawing little bubbles for the partition, I'm going to draw it as the sample space just being broken up into these pieces, something like this. So there's no overlap between any of the B1 through B5, and they make up the whole sample space. They make a partition. So then if you have A in green here as some event, well, then what this is saying is that I can break it up into, so this would be like A intersect B2, and then this would be A intersect B3, A intersect B4, and A intersect B5. So I could break it up into these four, I don't even need B1, these four non-overlapping parts. And so you could write A like that instead. Okay, so A is an event. Then we can break it up to non-overlapping parts by using each BI. Okay, so then we can do the probability calculation. Probability of A, I can now break it up into the probability of each intersection added together, because they're all, each of the parts are disjoint from each other. So you can do something like this. So this gives you a formula for calculating the probability of A if you know the probability of A intersect each of the parts. So if you know this piece, this piece, this piece, and this piece, then you can just add them up together to get the probability of A. But you may not know these things. We might know something else. So it's good to have another formula too. So we may not know each of these B, A intersect, or sorry, P probabilities. So you may not know each of these probabilities. And instead, we might know some conditionals. So we might know each probability of each part of the partition. So we might know each of these areas, or these probabilities. We might know that. We might know all of these independently or something. Okay, but that's not enough to tell us about the green area. But if we know conditional probabilities, then what we know is the proportion of this, for example, within the greater B. That's what the conditional probability is. So if we know each of these and we know the conditional probabilities, which is the proportion of A inside of each of the BIs, then we could put those together, because remember that those two are related to this, to get another equation. So then use that probability of the conditional A given B is the probability of the intersection. So how much of A is inside of the B divided by the probability of the BI. And then we're going to multiply over. So just multiply that up. Oops. And then we'll get a different formula for each of these intersections, which is the probability of BI times the conditional probability of A given BI. So this will give us the law of total probability. Okay, so I'll just call this a theorem. The law of total probability. So if we have a partition of omega, and A is another event, then you can write the probability of A as, so instead of doing the intersections, what we're doing from up here is we're replacing each of these intersections with this multiplication here. So it's going to be probability of B1 times probability of A intersect B1 plus the next one, probability of B2 times the probability of A. Oops, that should be a given. Sorry, over there. Given, I think I said the right word. Okay, A given B2 now. And so on until you get to the last set of the partition, En times probability of A given Bn. Or using fancy summation notation to make everything a bit nicer, you add up all of the things from 1 to n where the indices are I, so you just do this. So this is saying the same thing. You just change the I into each number from 1 to n, and you add them all up, and then you get the same thing as I wrote above. So this is called the law of total probability. Okay, so we can use this. Let's do an actual example. Okay, so suppose we have 2 buckets. Okay, so bucket 1 has 3 red balls and 2 green balls. Bucket 2 has, let's do 4 reds and 6 green balls. Okay, and then lastly, let's suppose the probability of choosing either bucket is 1/2. So you can draw a nice little picture for something like this to help you. So we got these 2 buckets. The first has 3 reds. So I'll just write like R, and 2 greens. And the second has 4 reds, 1, 2, 3, 4, and 6 greens. 1, 2, 3, 4, 5, 6. And so each has a probability of 1/2 being chosen. So we can do something like this now. What is the probability that bucket 2 is selected, then a green ball is chosen? Okay, so let's tackle a problem like this. First, we got to make events to make everything very clear. So what are the events, and is there a partition? So the partition, if you just think about this as I'm just going to choose a ball randomly, then you can say I'm either going to choose the balls in bucket 1 or bucket 2. So if you make A be pick a ball from bucket 2, then A complement will mean that I picked a ball from bucket 1. And you don't have to use A and A complement, but they are complements. You can name them like A and B or something if you want, but they are complements because you have to do one or the other. They're opposites of each other. So I needed a name for picking bucket 2 because of this part of the question, but I also need a name for picking a green ball. So let's call that B. So the names that I use in the definition of partition were B1 to Bn, but they're just names, so you may end up using different names when you actually do a problem. Okay, so B is going to be pick a green ball. So these are events that can happen in this little game where you have a bunch of balls and buckets and you pick a ball. Okay, so then this question, in terms of these labels, is asking for the probability of picking a ball from bucket 2 and picking a green ball. So it's really looking for this. And we can use our theorem. So we don't really need the partition stuff for this part of the question. This is just the simpler formula of conditional probability is but then manipulated. So maybe I'll start from here instead. So we know something like this. And then we can multiply this guy up. Oops, that should be an and there, sorry, or an intersection. So you can multiply that up, or maybe this one is more useful depending on the label, but it's the same on the top there. Okay, so what do we do? So either of these will let us solve for this, which is what we're looking for. So we're really looking for probability of A picking a ball from bucket 2 and picking a green ball. Okay, so which one is more useful? Well, it might be easier if I wrote down the probabilities of these. So let's see. So actually, this one is quite hard to write. So instead, what I should do is I should think about which one of these do I know better. So let's do that. So this is how to problem solve sort of on the spot. So we should see whether we know this one or this one. So what are these? Probability of A given B is the probability that I choose bucket 2 given that we picked a green ball. So that's a bit harder. The other one is the easier one. So this is the probability that we pick a green ball given we picked bucket 2. So this one we can actually just do by counting. So the probability of picking a green ball, given that we're already in bucket 2, all we have to do is look at bucket 2 and see that there's 6 green balls out of a total of 1, 2, 3, 4, 5, 6, 10, right? So there's 6 green balls out of 10 total balls in there. So it's 6 out of 10. So because I know this one, and I don't really know this one, which is a bit harder, I can now think about which formula I should be using, and it's this one. So then probability of A and B, I can get by doing probability of A times probability of B given A. Now what's probability of A? Probability of picking a ball from bucket 2, well, that's told to us as a half. Each bucket is equally likely to be chosen. So that's going to be 1/2. And then this was the 6 over 10. And so you can simplify if you want, but that's also fine like that. Okay. So it's a lot of it is just parsing the information you have. You have tons of information and you just have to know what you need to use. Okay, so let's do another example. If we just want the probability of selecting a green ball, then we can use the law of total probability. So selecting a green ball, that was event B. So if I want the probability of B, I can use the fact that A and A complement are a partition of the sample space, because the two events are pick bucket 2 or pick bucket 1. Those are complements of each other, and all the outcomes are in either one or the other of those two events. So they partition the sample space. So then I can use the formula I wrote down earlier. So the probability of an event, if you have a partition, is the probability of each part in the partition times each conditional. But here I only have 2 events in the partition, whereas in the general formula you could have n. So that's why in this example, there's only 2 things to add together. Okay, but we have all of these. So the probability of picking bucket 2 is 1/2. And the probability of picking bucket 1 is 1/2. So those are just 1/2 and 1/2. What about here? So this is the probability of picking a green ball, assuming you're in bucket 2. That's the 6 out of 10 from before. But then this one is the probability of getting a green ball given you're in bucket 1. So what's that going to be? Well, now we have to go back up to bucket 1 and just count a bit. So if I'm in bucket 1, there's 2 out of 5 greens. So I just put that in and then we're done. And again, you can simplify it if you like. Okay, so then the last type of example, which is the weirdest type, is when you reverse the conditional probability. So we can also find the probability that a ball was picked from bucket 2 given that a green ball was selected. So now we did the experiment, we got a green ball, and we want to know what was the probability that it was picked from bucket 2. So it's the conditional probability where we're picking bucket 2 given that we picked a green ball. So that's what we're looking for here. So we just have to use these formulas that we've put up earlier. So let's see, let's think about this one. So what can we say? All right, well, we know that the conditional probability formula is this. And luckily, we just figured this one out. So then we're basically done. Except, I think, did we do this one earlier too? Yes. But, so we know these. So we could just plug them in and get the answer. But there is one more interesting way to think about it. Which is going to come up in a second anyway, so we might as well do it. So if I multiply the P of B over, I solve for that. But as we've said a couple of times now, this guy, the intersection, can be written in two different ways, because you can also do probability of B given A is the probability of the intersection divided by the probability of A. So then if you multiply the probability of A over you get this relationship. So this is another way to solve for the probability of A given B if you know the probability of B given A. All I have to do is divide. And we know all of these things. So we just figured out the bottom one. So what was that? That was this thing. Let's see what that is. 1/2 times 6 over 10 plus 1/2 times 2 over 5. Probability of A, probability of choosing the bucket 2, that's just a half because both probabilities have 1/2, both buckets have 1/2 probability of being chosen. And then probability of B given A is the probability of that we got before, the probability of getting a green given that you're in bucket 2, that was the 6 out of 10. Okay, so then you can simplify this if you want, but that's that. Okay, so this little trick here is an example of Bayes' rule or Bayes' theorem. But the other thing I want to point out is that the probability of picking bucket 2 as 1/2, it's not the same as the probability of picking bucket 2 knowing that you already have a green ball chosen, which is what this thing was. That's not going to end up being 1/2, whatever it simplifies down to. Okay, but in any case, next we want to talk about Bayes' rule, which is this example demonstrates, and it basically using the conditionals in the other order to find the conditional in the order you want. So relating probability of A given B to probability of B given A, but then combining it with the law of total probability, we get a much bigger and more helpful formula. Okay, so let's state this. Bayes' rule, named after a mathematician Bayes. Okay, so suppose the events B1 to Bn, partition your sample space again, partition. Then if A is an event, we can write this. So this is the first form. So the idea is that we can relate the conditionals to each other. So any part of the partition you want, given A. So in the previous example, this was like bucket 1, given green, and the names were reversed. Okay, and that's equal to, so this just comes from doing this trick up here. It's just this formula, but with BI instead of B. So all you do is relate them both to the intersection and then divide by one of them, and you get this. Okay, so that is what we just used in the previous example. So again, it really comes from using this fact, which is that you can relate the intersection to two things at the same time. And then you can just divide over. Okay. So then we can use the law of total probability to make it seem much more complicated. So what we're going to do is we're going to replace probability of A. So we're going to replace this with what we learned before, which is this summation. So because the B's form a partition, I can rewrite this, I equals 1 to n, as this sum of probabilities times conditionals. Okay, so then that's what we're going to do here to get the more advanced Bayes rule. So as long as you know all of the conditionals in the reverse order, so if you know all the A's given BI's, sorry, the A given BI's, if you know each of those and you know the probability of each BI, then you can use this to calculate the probability of BI given A instead. Sure it's the right way. Okay. Oh wait, sorry, that should still be A given BI. Okay. All right, so let's see if we could put this into action. I'm gonna pause while I write down this long word problem to save some time. Give me a second. Okay, so here's the problem, a lot to take in. Basically the same as before, but we have a biased coin where heads is twice as likely to appear as tails. And when it's on heads, you pick a chip from bucket 1, which has 3 white chips and 4 red ones. When it lands on tails, you pick a chip from bucket 2, which has 5 white chips and 3 red ones. So you're still picking things out of buckets, but this time instead of the probabilities being half and half of which bucket you choose, they're determined by this biased coin. And the question is to find the probability that given a white chip being picked, what is the probability that the coin came up tails? Okay, so I'm going to try to use the notation that I used in the theorem so that everything stays the same this time. So what are we trying to find? We're finding the probability that given a white chip was picked, so I need the event that a white chip was picked. Given that, what is the probability that the coin came up tails? So here, what I'm going to do is I'm going to create my partition as B1 and B2, even though they really are, again, just complements of each other. So I could just say B and B complement, but I want to use the index notation just for practice. Okay, so I'm going to say B1 is that the coin was heads, and B2 is that the coin was tails. So remember, that's exactly the same because the coins determine which bucket you choose. That's exactly the same as saying that the chip was from bucket, I forget which one was for heads, but when it lands on heads, you get bucket 1. So chip was from bucket 1, and this is the same as saying that chip was from bucket 2. Okay, so then what we're trying to figure out is the probability that we got a white chip given that, oh wait, sorry, other way. Probability that we got tails given that a white chip was picked. So that means we want to know the probability that tails came up, which is probability of B2, given that a white chip was picked. This is our ultimate goal, to figure out what this is. Okay, so what are some things we can say that might help us? First, what's the probability of the coin being heads or the coin being tails? So we can get the probability of each event in the partition, which will help a lot. So if heads is twice as likely as tails, that must mean it has to be 2/3 and 1/3 for the coin. So that's the first trick to know. And what else? And B1, B2 form a partition of the sample space because all the chips are either in the first bucket or the second bucket. So you have to pick one from one or the other, and there's no overlap between the buckets. So they form a partition. Okay, so then we can use our theorems that we know about. What else can we say? Well, we can say a lot of stuff about probabilities of getting chips once we know what bucket we're in. So if I know that I'm in bucket 1, I can find the probability of getting a white chip. That's not so bad because I just look at bucket 1 and I see what's in it. So bucket 1 has 3 white chips and 4 red ones. So that's 3 out of 7 chance that I get a white one if I'm already in bucket 2 or bucket 1. And then I can also do bucket 2. Same idea. I just go and look, okay, there were 5 white chips and 3 red ones. So 5 out of 8 of them. So that's the chance of getting a white chip if I'm already in bucket 2. So with all this information, I can now use Bayes' rule because I have all of the conditionals in the reverse order. So I can figure out the conditional of B2 given A because I know the probability of B2. I know the probability of A given B2. And I also know the probability of A given B1. So that's, I need all of that. I also need the probability of B1. So as long as I have those, then I can use this equation. Okay, and we have all this. So now we just plug it all in. So probability of tails was 1/3. Probability of A given tails was 5/8. Probability of heads was 2/3. Probability of getting a white chip if you're already in bucket 1 is 3 out of 7. And then this is the same as on the top. So you get that. Okay, so then that's what we're looking for. All right, so let's do one more example. For this example, I'm just going to draw a picture just to speed up all of the writing. So let's just suppose we have 3 buckets this time. And what do we got in here? Let's do red, blue, blue, red, red, blue, blue, red, 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 blue, blue. And let's say box 1 has probability 1/6 of being chosen. Box 2 is probability of 2/6. And box 3 has probability 3/6 of being chosen. So let's do something like find probability of choosing red, find the probability of choosing box 3 given we selected blue. Okay, so first thing is we need to partition. So whenever you have these bucket problems, the partition is glaring right at you. The partition is that you can only be in one bucket or another, so there's no overlap between the outcomes. So the partition, I'll call them B1, which is choosing the ball from the first box, B2, choosing the ball from box 2, and B3, this time there are 3 instead of just 2 sets, so it's not just something in its complement, choosing ball from box 3. Okay, so you either choose a ball from box 1, box 2, or box 3. There's no overlap, and they make up everything in the sample space, so they are a partition of the sample space, these 3 events. So then we know the probability is associated to each event in the partition. What you need to use Bayes' rule. So we might as well write those down. Those are just given to us up here, 1/6, 2/6, 3/6. Okay, so let's make a name for this. Probability of choosing red. Let's call that, I'll do it down here. I'll do it here, I guess. A is choose a red ball. So then probability of A, we can use the law of total probability. So Bayes' rule is when you're trying to find something given something else in a different order. But if you're just finding the probability of an event, you can use the law of total probability as long as you know all of the conditionals, which we do. Okay, so it's probability of B1 times probability of A given B1 plus probability of B2, probability of A given B2 plus probability of B3 times probability of A given B3. And we know all these things. So this is 1/6. What's this? This is just the probability of choosing a red ball given that you're already in bucket 1. So you just have to go count and say there's 1 out of 3 red ones. So that's what goes there. Probability of B2 is 2/6. All right, how many red balls are there in bucket 2? 2 out of 4. So that's the probability of picking a red one given that you're already in bucket 2. And then lastly, 3/6 times, this was 3 out of 5. Okay, so that's that. All right. And then, so that's the first question. So now let's do the second. The probability of choosing box 3, given that we selected blue. Well, I need a name for selecting blue in the first place, so let's call that C. So this is select blue one. So then what we're trying to find is the probability that we chose bucket, what was it? Bucket 3, box 3, given that we selected a blue ball. And so this is going to be Bayes' rule. Previous one was law of total probability. So first, we just relate it using the proportions that both relate to the intersection. So this is how Bayes' rule starts. So it reverses the conditional, and then you divide by probability of C. But then the whole point is this one, I don't know without using the law of total probability. So really Bayes' rule is just the law of total probability on the bottom here. So if this was A instead of C, if it was selecting a white ball, then we would already have this bottom because it would just be this thing up here. But now we sort of have to do it again. Okay, so probability of B3 was 3 out of 6. The probability of selecting a blue ball, if you're already in bucket 3, well, there's 2 out of 5. So that's 2 out of 5. And then on the bottom, we used the law of total probability, like I said. So I don't know the probability of C, but I do know the probability of each event in the partition, and I can calculate the probability of C given each probability in the given each event in the partition. So I can do this again, just like what we did for the previous part. Okay, so that's all in the denominator. Probability of B1, that was 1/6 times something, plus probability of B2 was 2/6 times something, plus probability of B3 was 3/6. Those I remember. The others I have to go look at the buckets again. So the probability of getting a blue ball, given that I'm already in bucket 1. So how many were there? There was 2 out of 3. How many were there in bucket 2? There was 2 out of 4. And this last one's actually the same as on the top. It's how many were in bucket 3, which is 2 out of 5. Okay, so that's going to be it for today. That's the last part. See you next time.